Hello everyone and welcome to the OneClass channel. My name is Donna and I'm a recent master's graduate from the Material Science program from the University of Ontario Institute of Technology, also known as Ontario Tech University. So today we're going to go over some commonly asked questions in chemistry at the high school, college, and university level. So if you needed any help with homework or with tutoring, then check out the links in the description below. Now let's just get started on our set of questions for today's session. Okay, so question 1 asks, how many valence electrons do chlorine, bromine, and iodine have? So chlorine, bromine, and iodine, they're all part of group 17, which are the halogens. So the halogens all have 17 valence electrons. So let's try to draw out an atom of chlorine. So chlorine has atomic number 17. So it also has 17 protons, and a neutral chlorine atom has 17 electrons. So if we were to draw out a chlorine atom and all of its electrons, there'd be 2 in the innermost shell, and then 8 in the next shell. So now we've drawn 10. So now in the outermost valence shell, you end up with 7. Let's do 8. Okay, so that's the chlorine atom. And all the other atoms in this group follow the same trend. So let's say we had bromine now, which has 35 electrons. Just to save time, let's change this to a bromine atom. And now the difference between bromine and chlorine is that bromine has an extra shell around it, which then has also 7 valence electrons. Okay, so if you count this out, you end up with 35 for bromine. Okay, and 18. Yeah. So let's see what the junior tutor said. We can consult the periodic table of elements to find out the number of valence electrons for these elements. Based on the periodic table, chlorine, bromine, and iodine belong to one group, which is group 17. Elements present in this group has 7 valence electrons, hence chlorine, bromine, and iodine all have 7 valence electrons. Let me just draw the last. Okay, so that was bugging me a bit. But this solution is correct. Okay, so question number 2. How many valence electrons does a phosphorus atom have? its group number is 5A, and its atomic number is 15. So this question gave us some helpful tips. Phosphorus is in group 5A, and there's a rule that when you're in group 5A, you have 5 valence electrons. And they also told us the atomic number phosphorus, which is 15. So that means in the neutral phosphorus atom, it also contains 15 electrons. So we can try to sketch out a phosphorus atom and show all of its different electrons. So there's 2 in the innermost shell. And then in the next shell, we draw in 8. So now we have 10 out of the 15. And for the valence shell, we just have to draw in 5. And you can see that there are 5 valence electrons. Okay, so the junior tutor said that the group number of an element is a big factor for us to identify the number of valence electrons present in the element. Problem already stated what group number phosphorus is located in. So for elements belonging to group 5A, all of them have 5 valence electrons. Hence, phosphorus has 5 valence electrons. Okay, so phosphorus is found here, and you can see it's in group 5A. So the solution is correct. Okay, so question 3 asks, how many milligrams are in a gram? Okay, so there are 1,000 milligrams in 1 gram. And we know that because of the prefix milli. So similarly, there are 1,000 milliliters in 1 liter, and so on and so forth. We are able to know how many of each, like we know that there's 1,000 in 1 gram because of that prefix. So let's try to do an example question. So let's say we want to find out how many milligrams are in 0.75 grams. So if we multiply 0.75 by the conversion factor with our desired units on the top and the units we're trying to get rid of at the bottom, so 0.75 grams times 1,000 is 750, and the units are now in milligrams. So there are 750 milligrams in 0.75 grams. Okay, so the junior tutors just said there are 1,000 milligrams in 1 gram. So the solution is correct. Okay, so question number 4. How many electrons does oxygen have in its valence shell? Its atomic mass is 16, and atomic number is 8. Okay, so they gave us some other facts about oxygen, atomic mass, and also atomic number. But what we're most interested in is atomic number, since atomic number tells us the number of protons. And if we have a neutral oxygen atom, then that means we also have 8 electrons. So now let's try to sketch out an atom of oxygen. So that's an O. And then this is the inner shell that is able to house 2 electrons. So the s orbital. And now we have 2 out of the 8 that are drawn. So I'm just going to draw in the remaining 6. And we can see here, since this is the valence shell, which is the outermost shell, oxygen has 6 valence electrons. So the answer is option C. So the junior tutor said that the electron configuration of oxygen is helium 2s2, 2p4. The valence orbitals are 2s and 2p. The number of valence electrons in oxygen is the sum of electrons in 2s and 2p orbitals. The electron configuration shows that the 2s orbital has 2 electrons and the 2p orbital has 4. Total number of valence electrons is the sum of 2 and 4. Therefore, the number of electrons in the valence shell is 6. Yep, so this is a different approach to answering the question. So this solution is correct. Okay, so question 5 asks, what is the molar mass of ammonia? And ammonia is NH3. So when we want to find the molar mass of a compound, it's just going to be the sum of all of the different molar masses of the atoms involved in that compound. And we also need to take into account how many of each atom are in the compound as well. So for example, the molar mass of ammonia is going to be equal to the molar mass of nitrogen plus 3 times the molar mass of hydrogen, since there are 3 hydrogen atoms in ammonia. So the molar mass of nitrogen is around 14.01 grams per mole. And the molar mass of hydrogen is 1.01 grams per mole. Okay, so if we add these values up, we get around 17.04 grams per mole for the molar mass of ammonia. So these values, the 14.01 and 1.01, so the atomic masses of these atoms, can just be found on your periodic table. And the junior tutor said that the molar mass of a molecule is the sum of the individual masses of the atoms present in the molecule. For the ammonia molecule, we have nitrogen and hydrogen. The molar mass of these elements are present in the periodic table and are listed below. For the ammonia molecule, there's 1 nitrogen and 3 hydrogen atoms. Hence, the molar mass of ammonia can be computed as the following. And then they plugged in their values and got around 17.03. Yep. So this solution is correct. Question 6. What are unicellular organisms and give examples? Okay, so let's try to, even if we just analyze the word unicellular, since there's a prefix of uni, we know that this means 1, and cellular, well, that just means like a cell. So therefore, unicellular means a single-celled organism. So these single-celled organisms are able to perform vital functions that are necessary for life. There's a lot of different examples of unicellular organisms. So I'll just list a few. You can have like a paramecium or amoeba, even yeast, or bacteria. Just to name a few. Let's try to sketch out a bacteria cell. So these thin like hair looking strands are known as pili. And then the tail of the bacteria is the flagellum. So even though these are unicellular, they all kind of looked slightly different if you're to look through them in a microscope. For example, this is like what a bacteria might look like. And amoeba, I always thought it looked like an egg, almost like it has like different things like this. I'm not a good sketcher. But yeah, these are unicellular organisms. And the junior tutor said that they are single-celled organisms or living organisms which are made up of only one cell. This single cell performs and regulates all the vital functions necessary for life. These organisms are very small, that they are mostly invisible to the naked eye. Some examples of unicellular organisms are bacteria, protozoa, algae, and yeast. Yep. So this solution is correct. Okay, so question number 7. Draw the Lewis structure of sulfur tetrafluoride showing all the lone pairs. Identify the molecular geometry. What is the hybridization? What are the ideal bond angles of this geometry? And is an SF4 molecule polar or nonpolar? Okay, so let's start off by writing the Lewis structure, since this will help us answer all of the following questions. So when writing out the Lewis structure, we first need to calculate the total number of valence electrons in this molecule. So in the case of sulfur, sulfur has 6 valence electrons, and fluorine has 7. And since there are 7 fluorine atoms in this molecule, there are 4 fluorine atoms in this molecule, we multiply this by 4, and we get a total number of 34 valence electrons. So now let's try to sketch out the skeletal structure of SF4. So sulfur will be our central atom, since it is the least electronegative. And then I'm just going to draw 4 single bonds to the fluorines. And I'll also draw in all of their lone pairs. Okay. So if we count out how many electrons I have so far, we have 2 electrons that are participating in the bond, and we have 4 bonds. And we also have 6 non-bonding electrons on our fluorine atoms. So we only have 32 out of the 34 electrons drawn. So for the remaining 2, I'm just going to add them as a lone pair on the central sulfur group. So this gives us our final Lewis structure. So now let's try to analyze this Lewis structure to find out its molecular geometry, hybridization, and the bond angles. So the central sulfur atom contains 1 lone pair and 4 bonded atoms. So now we can use a helpful VSEPR chart to help us answer all the following questions. Okay, so this is a VSEPR theory table, and you can see that when you have 1 lone pair and 4 bonded atoms, this is on the next page. Yep, so right here. When we have 1 lone pair, 4 bonded atoms, we have a seesaw molecular shape. And we also have a trigonal bipyramid electron geometry. And this chart also can show us the hybridization. So it is sp3d hybridized. And another way we can find out its hybridization is by counting the number of charge clouds. So charge clouds can be the lone pair and also the bonded atoms. So we count out 5. And when you have 5 charge clouds, this is sp3 dehybridized. And finally, the bond angles are 90 degrees and 120. Okay, so that answers the first couple parts of the questions. And is the SF4 molecule polar or nonpolar? Okay, so to determine whether or not a bond is polar, we need to find out the electronegativity values of the atoms that are involved. So let's find out the electronegativity difference between a sulfur and a fluorine bond. So fluorine has an electronegativity value of 4, and the sulfur has an electronegativity value of 2.5. So this tells us that the difference in electronegativity is 1.5. So therefore, we can say that the bond is polar, and this is because our electronegativity value is greater than 0.4, but it's less than 1.7. That's another way we can tell if a bond is polar or nonpolar. And we can also show these as dipole moments on our molecule. So since fluorine is much more electronegative than the sulfur, we can show these dipole moments like that. But due to the lone pair, then these dipole moments don't cancel each other out. So we'll actually have a net dipole moment kind of going towards all of the fluorines, like that. Oops. So we can say that we have a non-zero dipole moment. And this is because of the structure of our molecule, which is trigonal bipyramid. So this tells us that sulfur tetrafluoride is a polar molecule as well. Okay, so not only are the sulfur-fluorine bonds polar, but also because they don't cancel each other out, we have ourselves a polar molecule. Okay, so now let's see what the junior tutor said. Step 1 is to list the elements, their valence electrons, and determine the total valence electrons. If a charge is present, then you would add the value of the charge to the total valence electrons when it's negative, or you would subtract it if it's positive. So we didn't have a charge on our compound, so we didn't need to do that part. And they found 34 valence electrons. They drew out the skeletal shape and showed all the lone pairs and got the correct Lewis structure. Okay, so now they determined the steric number. So this is the same thing as adding the number of lone pairs with the number of bonded atoms, and they got 5. And when you have a steric number of 5, it is sp3d hybridized. The electron pair geometry is trigonal bipyramid, and because there was one lone pair, we have a seesaw molecular geometry. So I think they summarized it down here. Seesaw. And since this molecule is asymmetric, it is polar as supported by the net dipole shown below. So they also showed how all the fluorines kind of are more electronegative, and the lone pair causes them not to cancel each other out. For this molecule, there are 2 bond angles present. For the equatorial fluorine-sulfur-fluorine bond, it's 120. Okay, so they showed that here. And for the axial equatorial fluorine-sulfur-fluorine, the bond angle is 90 degrees. So therefore, it has molecular geometry like a C-star. The sulfur is sp3 dehybridized. 2 bond angles are 120 and 90 degrees. And since it's asymmetric, it has a net dipole, and thus it is a polar molecule. Yep, so this solution is correct. Okay, so question number 8 is, what is the Lewis structure for the ammonia molecule, which is NH3? Be sure to include all resonance structures that satisfy the octet rule. So when writing out the Lewis structures, we first need to calculate the total number of valence electrons for this molecule. So in the case of nitrogen, nitrogen has 5 valence electrons, and hydrogen contains 1. And since there are 3 hydrogen atoms, we would multiply this value by 3. And if we were to add them up, we would find a total number of 8 valence electrons. So now let's start off by writing out the skeletal structure of NH3. So nitrogen would be our central atom, not because it's more, in this case, it is actually more electronegative than the hydrogen, but the fact that it's able to form multiple bonds makes it more likely for the nitrogen to be the central atom compared to our hydrogen. So hydrogen can only form 1 bond. So now that we know nitrogen's our central atom, we can draw its 3 bonds to hydrogen. And if we recall that each bond contains 2 bonding electrons, and we have 3 bonds, we only have 6 electrons drawn so far, so we need to put the remaining 2 electrons on our nitrogen. Okay, so this gives us the final structure, or the final Lewis structure of NH3. So we can also find out the type of molecular shape it has by looking at the number of charge clouds. So by charge clouds, I mean the lone pairs and the bonded atoms. So we have 1 lone pair and 3 bonded atoms. So if we use a VSEPR table, we can find out the type of shape it has and electron geometry. So when you have 3 bonded atoms and 1 lone pair, this tells us we have a trigonal pyramid molecular shape. And it also tells us that we have a tetrahedral electron geometry. We also have an sp3 hybridization. And the bond angles would be 109.5 degrees. Okay, so the junior tutor said And we weren't able to include any resonance structure since it was not applicable for this molecule. So to write the Lewis structure, first find the possible skeletal structure. Okay, so they found nitrogen will act as the central atom. And then they drew out all the bonds and showed the one lone pair on the nitrogen. No resonance structure can be written for this molecule since the lone pairs can only be contained in the nitrogen atom. Yep. So this solution is correct. Okay, so question number 9. Calculate the molar mass for sodium sulfate, Na2SO4, and a sample of sodium sulfate with a mass of 300 grams represents what number of moles of sodium sulfate? This is a two-part question. So first we need to find the molar mass of sodium sulfate. And to do that, we need all the different atomic masses of the atoms involved in the compound. And we also need to take into account how many of each atom is in sodium sulfate as well. So for the molar mass, it's going to be 2 times the molar mass of sodium plus the molar mass of sulfur plus 4 times the molar mass of oxygen. So all of these molar mass values for these different elements can just be found on your periodic table. So in the case of sodium, sodium has a molar mass of 22.99 grams per mole. Sulfur has a molar mass of around 32 grams per mole. And finally, oxygen has a molar mass of around 16 grams per mole. So now if we add all these values up, we get a final molar mass of 142 grams per mole. Okay, so that's for part A, where capital M is molar mass. And when we solve for part B, we know the mass is 300 grams. What are the number of moles of this amount of sodium sulfate? So to answer this question, we'd use the equation number of moles is equal to mass over molar mass. So the mass was 300 grams. And we calculated the molar mass in the previous step to be around 142 grams per mole. So 300 divided by 142 gives us 2.11 moles. So you'll notice that when we divide mass by molar mass, our grams will cancel out and our moles becomes our unit. Okay, so now let's see what the junior tutor said. First, they calculated the molar mass of sodium sulfate. They determined the elements and how many atoms of each are involved in the compound. So there's 2 sodium atoms, 1 sulfur atom, and 4 oxygen atoms. Step 2 was to determine the mass contribution by each element by its molar mass with the number of atoms there are. So they summed up all the different molar masses of the elements, and then they multiplied it by however many atoms there are. 23 times 2, 46. 32 times 1 is 32. 16 times 4 is 64. Step 3, add the mass contribution of each element to determine the molar mass. So 46 plus 32 plus 64 is 142. So they did it in multiple steps. I just fit all of mine on one line. But if you like to show all the different steps, then you still get the same answer, which is good. And then a sample of sodium sulfate with a mass of 300 grams represents what number of moles of sodium sulfate? So to determine how many moles there are, divide the given mass of sodium sulfate with its molar mass. So 300 divided by 142 is 2.11 moles. Yep, so this solution is correct. Great explanation. Okay, so question number 10 is to give the full electron configuration of iron. Okay, so when writing out the electron configuration, there are different steps that you can take in order to write the full electron configuration. So step 1 is to divide your periodic table into the different orbitals. So S, P, D, and F. And I can show what that looks like. Like so. And you kind of get something that looks like this. So for the leftmost columns, this is the S block, including helium. And this green section is the P block. And the middle transition metals is the D block. And the last two rows, the lactanides and actinides, is the F block. So now, starting from hydrogen, we move left to right across the periodic table until we get to our desired element. And then we write the row number followed by the block letter. And then in the superscripts, we show how many electrons are in each of those orbitals. Using superscripts. Okay, so I'll also add that when we get to the D block, we write the row number -1. And when we get to the F block, we write the row number -2. Okay, so now let's try to do our example, which is iron. So iron is found here, right in the middle of the transition metals, atomic number 26. So starting from hydrogen, we move left to right across the periodic table, and we write the row number, which is 1, the block letter, which is S, and then we write how many electrons are in this 1s orbital. So in this case, there can only be 2 electrons in an s orbital. So we write a superscript of 2. And this only brings us to the electron configuration of helium. But now we move on to the next row. So row number 2, the block letter is 2s, and then there are also 2 electrons in that orbital. Then moving over to the p block, we're still in row 2, and we write p, and a p orbital is able to have 6 electrons. And now moving over to row 3, s2, and then 3p6, and then we can move on to the next row, which is 4s2, and then iron is in 3d, and then we count how many electrons up to the iron. So we count 1, 2, 3, 4, 5, 6. So we write 3d6. So this is the full electron configuration of iron, but we can also write the shorthand configuration. So when writing the shorthand configuration, we write the noble gas that comes before iron in square brackets. So in this case, it's argon. And then we just continue on writing the remaining electron configuration as normal for S2, 3d6. Okay, so let's see what the junior tutor said. In writing the electron configuration of an element, we follow the Aufbau principle shown below, which states that the order of energy will dictate the order in which electrons are arranged in their orbitals. Therefore, the lowest energy will be occupied by electrons first. So this is a different method of writing electron configuration. So it just depends on what you're comfortable with, but you can write all of the 1s up to 7 in a column, and then kind of align it with the 2p up to 7. The 3 goes up to 6, and then 4 goes up to 5. And then to find out the order, you kind of go diagonally like this, and you can still get 1s, 2s, 2p, 3s, 3p, and then 4d or 4s, and so on and so forth. Remember that each orbital can hold a different number of electrons. The s orbital can hold 2, p orbital can hold 6, the d orbital can hold 10, and the f orbital can hold 14. So since iron has 26 electrons, using the Aufbau principle, they wrote out their electron configuration. Yep. So this solution is correct. Okay, so which of the following statements concerning xenon tetrafluoride is true? So they already have the Lewis structure given, so let's write that down as well. We have xenon as our central atom, and then 4 single bonds to these fluorines, and then each fluorine has 6 non-bonding electrons. And then the remaining 4 electrons are on the xenon central atom in the form of a lone pair. So now let's see the options they give us. Which of these statements is true? Electron geometry is octahedral. Molecular geometry square planar. The bond angle is either 90 degrees or 180 degrees. And this molecule is nonpolar. Okay, so let's start off by counting the number of charge clouds that are on the central atom. which is xenon. So by charge clouds, I mean the lone pairs and also all of the bonded atoms. So we can see that the xenon contains 2 lone pairs, and there are also 4 bonded atoms. So using a VSEPR chart, we can find out its molecular shape and electron geometry. So this should be on the next page. So when we have 4 bonded atoms and 2 lone pairs, we get a square planar molecular shape. And we also get an octahedral electron geometry. And the hybridization is sp3d2. And the bond angles for all of the bonds is 90 degrees. Okay, so we also need to find out whether or not this molecule is polar or nonpolar. So the steps in finding out whether or not a molecule is polar or nonpolar is to first find out if we have any polar bonds. So to find out if a bond is polar, we need to calculate the electronegativity difference between xenon and fluorine. So now let's look up the electronegativity values for both xenon and fluorine. Okay, so these show all the different electronegativity values of the elements. So fluorine has an electronegativity value of 4, and xenon has an electronegativity value of 2.6. I think these are a bit rounded, but if we were to subtract 4 minus 2.6, you get 1.4. So therefore, we can say that the bond is polar, and this is because our electronegativity difference is greater than 0.4, but it's less than 1.69. So let's draw out dipole moments towards the fluorine to show that they're more electronegative. But if we look at the structure of our molecule, you'll see that we have the 2 lone pairs, can kind of be drawn like that. So because of this symmetrical shape, the overall molecule is nonpolar. So I can say that xenon tetrafluoride is a nonpolar molecule, and the reason for that is because the dipole moments that are caused by the fluorine are cancelled out. So the dipole moments cancel each other out. And another way of saying this is that we have a 0 net dipole moment. And we can say this is because we have a symmetrical molecular shape. Okay, so now let's see what the junior tutor said. Well, first we had to look at these different statements. So electron geometry is octahedral, so that's correct. Molecular geometry is square planar, which is correct. The bond angle is 90 degrees, so I guess that's correct, because I said either or. And then finally, it is nonpolar. So that is correct as well. So it's option A. Okay, so the junior tutor said that the properties of a certain molecule, such as electron and molecular geometry, bond angle, and polarity, can be determined from its steric number, or the number of atoms bonded plus the number of lone pairs attached to the central atom. For a molecule of xenon tetrafluoride based on the given electron dot structure, we have 4 atoms bonded plus 2 lone pairs attached to the central atom. Thus, it has a steric number of 6, which corresponds to the following: octahedral electron geometry, square planar molecular geometry, bond angle of 90 degrees. I would just say it's, yeah, I guess it could be 180 if we look at the bond angle between the 2 electron groups, the lone pairs. And the molecule is nonpolar because of its symmetry, which cancels out any dipole moment. So the correct answer is A. Yep. So the solution is correct. Okay, so those are all the questions for today's session. And if you enjoyed today's Q&A and you'd like to be notified of when we do this next, please hit the subscribe button and notification bell below. And if you'd like to submit a question of your own, then check out the links in the description. And also, if you enjoyed today's video, you can give it a like and a comment, and share it with your friends and classmates if they needed any help with chemistry. This has been Donna from OneClass, and I hope to see you soon. Bye.